Okay. So. Yeah, I told y'all to spec some chips, and then I want to just like look at them a little bit, and then maybe we could pick one or two or not, and then introduce ourselves into a KiCad workflow I want to try. Okay. I'm going to put an asterisk on like the KiCad workflow because I kind of know how I want this to work. I don't know mechanically how to make it happen. Like I don't know what buttons to press to for what needs to happen, but I know we can do it. So yes, it'll be a learning experience for all of us. Okay. So let's just go down the list and look at some data sheets. Okay, we're looking at a TI regulator. You can't go wrong with a TI buck chip. TPS. Okay, I just jumped to something that I remembered that would be very useful. It'd be good if we also have a buck with the buck chip we use on formula as like a control group. So if we know we're actually making improvements. I forget what the number is, 2561 or something. I don't remember. 5621, regardless. All right, let's look at this guy. So 4.5 volt to 17 volt input, 2 amps, synchronous step down voltage regulator, 6 pin. Okay. So looks like a pretty standard buck. So something I'd immediately be a little bit suspect of here is the input voltage range, which is 4.5 volts to 17 volts, because our LV battery can go up to 18.8 volts, which is slightly higher than 17 volts. But when it comes to like speccing out regulators for this kind of thing, I would highly, highly recommend just having a huge margin for your input voltage. Like you could probably find something that could do a similar job that could take in up to like 32 or like 36 volts. But yeah, this is something to keep in mind. Maybe if we decide to do something where we're stepping down in 2 stages, this could make sense, but also I don't think it makes sense to have 2 buck converters in like series. Okay. Pulse, skip mode, or continuous current mode. Interesting. So I vaguely know what this means, but the equations are different for calculating like your output current when you're in pulse skip or continuous current. So you might otherwise hear these be called as CCM, continuous current mode, or DCM, discontinuous current mode. And I don't know if I can explain the difference properly, but I just know that the equations are different for these 2 things. So I guess there's 2 types of chips here that we get to pick from. Switching frequency is kind of like on the lower range. Not super slow, not super fast. I'd say like right in the middle of the ballpark of what you could expect. Startup from pre-biased output voltage. Okay. Sure. Maybe we could read a little bit more in the data sheet to see what that means. Cycle by cycle over current limit. Okay. So this is a pretty cool feature. What I think this means, and again, we have to read the data sheet, is that every duty cycle, when it switches on and off, it's going to see if it's outputting anything higher than its like rated limit, which means it'll shut itself off ideally, or it'll send some signal that might tell a microcontroller to shut it off or something, which is great for safety. Because if you're not expecting your load to ever exceed 2 amps, and all of a sudden you're seeing 2.1 amps, 3 amps, 4 amps, whatever, you know there's probably like a short circuit on your load, or there's an issue with your regulator. Non-latch under voltage protection. I don't know what TSD is. TSD protection. Oh, okay. Over temperature. I don't know what it stands for. Short time? Oh, time short over
Thermal shutdown.
yeah, maybe. I don't yeah.
The first. Oh,
Oh, yes. Nice. Nice. Okay, cool. So it has some sort of capability for um, temperature sensing. Maybe it's internal. Not really sure yet. Fixed soft start, 1 millisecond. This is kind of just like a function of switching regulators. Generally, they need to be fed in some input voltage, and then to get themselves actually like regulating properly, they usually have some internal voltage reference. They usually have like an LDO, like a LINREG, or something internal that has a fixed voltage, and that needs to be charged up or like powered on to what we'd expect, so that it itself knows whether it's doing the correct job regulating. That might have not been clear, but I think if we scroll down the data sheet, there's like a diagram that might make it a little bit more clear. But yes, soft start is kind of just like this ramp up in voltage on the specific pin for most switching regulators. Usually it can, like, or not usually, sometimes it's combined with a feedback pin, which might actually be what we're seeing here. But yeah. So what I'm kind of doing right now is walking through how I'd approach a data sheet if I were to see a new part. First, read the features, number one. You could probably easily sift out something you don't want if you just see that like the output voltage range is not what you'd expect, or it's like missing some key feature you really wanted for your design. It's a good first pass vet. Simplified schematic can be a good reference. Like, it's not very useful. There's usually an application note much further down, which will tell you like exactly what parts to use usually, which is pretty nice. So this is cool. We could see the efficiency, and honestly, the current load of the sensing boards and sensing stuff will be pretty low. That's something that there's a spreadsheet that exists somewhere that we need to take a look at again. But that's something we should keep in mind. I think 2 amps is way higher than what we'd expect or what we'd need. Regardless, we get to see like efficiency at different loads. And if we decide, or if we know, oh, we only need 50 milliamps of load current, where does that get us? That gets us like right here. Where does it go on the efficiency graph? For our V out is 5 volts. It'll still be pretty damn high, like around 90%. Not bad, not bad. But like if our load current is like any smaller, if it's like 10 milliamps, and I'm getting this value because this is 10 milliamps. It's like 80%, could be worse, but it's not great. And if it's any lower than that, it's just going to be pretty disastrous at that point. Okay, now here, I love this part of data sheets. It like basically takes this and then goes one step deeper. So you don't really have to like know what's going on to kind of understand what's going on here. Okay, so this is a 6-pin package, cool. Sometimes the package type matters. For formula, we usually go for packages where the pins like stick out so that we can like solder or rework them if we need to. But in the power electronics world, sometimes it's advantageous, not sometimes, it's definitely advantageous to have components with high currents flowing through them to have QFN packages. QFN, I don't know what it stands for, but it means like all the pins are like underneath or inside. It's not very easily accessible. And that's for better like thermal conduction between the solder pad, the solder, and the chip itself. Okay, so let's look at these pins. We got a ground pin. It's pretty self-explanatory. Low side power NFET, as well as ground terminal for controller circuit. Okay, connect sensitive V feedback to this ground at a single point. Okay. So y'all remember how feedback works? Can someone explain what the controller is kind of looking for? And you could pick like an arbitrary number, but hopefully you'll remember. let's say we have our buck, right? And then this is our V out. The switch node is the same node as V out. So just know that. And then you usually have something in between here. I'm not going to tell you what it is. And then you connect to V feedback. Like, what do we want to see at V feedback usually?
Like 1 volt.
Yeah. It's usually 1 volt, maybe 1.2 volts or something. But this middle part here is a resistor divider. And you can configure that such that your output voltage times resistor divider transfer function ends up with 1 volt here. So that's how, like, that's why these chips like actually have a variable output range and it's not fixed to one specific output voltage. If a chip does have a single output voltage, it likely means that there's an internal like check comparator or whatever checking the output voltage. Okay, V in, input supply voltage pin, drain terminal of high side power FET. Okay, V feedback, converter feedback input, connect to output voltage with, okay, yeah, there it is, resistor feedback network. Enable input control, active high and must be pulled up to enable device. Okay, that sounds kind of dense, but basically it means that it needs to be high, and in the data sheet it'll tell us what voltage that is exactly, and must be pulled up, so to some voltage, to enable the device. So that means that this will only switch when this is pulled high, which is cool. On formula, we don't really play with this pin that much. We just connect V in to enable, which means that anytime the battery is connected to any of our boards, it's automatically switching. But maybe there's a use case where you don't want a power rail enabled all the time. You only want it enabled sometimes. You can set up some kind of control circuit on the enable pin so that it turns on when you want it to. VBST, connect input to high side and FET gate drive circuit, connect one. Okay, cool. So this is the bootstrap pin. And I'll talk a little bit about how bootstrapping works. So it's worth noting that this is a synchronous step-down converter. Do y'all remember what the difference, like the simplest difference between an asynchronous and synchronous buck converter are? There's a key difference.
Did the synchronous ones have a diode?
Close, it's the opposite.
Oh, shit.
Asynchronous has a diode for conduction on the lower leg, and asynchronous has another FET. So asynchronous means you're only switching one guy, but synchronous means you have to control both of them, like 2 different FETs. You have to synchronize, hence the name. Yeah.
Right?
Yeah. So if I were to draw what's happening here, oh my God, it's very hard to draw with a trackpad. Let me try that again. This is a catastrophe, I'm sorry. This is very ugly. Okay. So we have 2 FETs. And they're connected to like a controller. And the controller controls the gates of these FETs. Do y'all know how FETs work? Like at a very, very low level. Like basically, if your gate to source voltage, so this is your gate, this is your drain, and this is your source. And then likewise, this is your gate, this is your drain, and this is your source. So the source of the top FET and the drain of the bottom FET are tied together. But I'll just draw this dotted line to make the distinction so we don't get confused. When
Adi,
yeah.
Adi, I just want to make a quick distinction. The drain and the source actually flip for a PFET.
Yes, but on this, we know that they're N-type
Oh,
MOSFET.
sorry.
Yep.
I'll shut up. Sorry, I shouldn't
Nope.
have said anything.
All good, all good. Yeah, so Lucky does bring up a good point. If you're looking at P-type MOSFETs or FETs, the drain and the source are flipped. It might not be intuitive, but since current is flowing this way, and the way we bias it and the way current flows in it, this is the source of positive, or this is the source of, is it the electrons or the, I don't know, this is the source of something. That's why it's called the source. I'm sorry, that was a pretty bad explanation. But regardless, on an N-type FET, we know it's N because it says the data sheet, drain is here, source is here, gate is here.
Wait, why would you use like an NFET versus a PFET? Like, could you use a PFET in this situation, and how would it look different?
So yeah, let me explain real quick. When you're trying to quote, like turn on your FET or allow it to conduct, your gate to source voltage is what matters. And when you say voltage gate to source, you'd express it like this, VGS, which means it's the potential difference from this point here to this point here. And you're like measuring down, basically. You want that, you want this to be positively biased. You want this to be like a positive number. Now, if you think about a P-type MOSFET, and you draw them like this with a little like deedly bob right there. You have gate, and your source and drain are flipped this time. Your voltage gate source has to be biased the other way. So the potential on your source has to be higher than the potential on your gate. But not important for right now. So we're trying to get this VGS to be some positive value, right? And I'll draw a little bit extra to make this a little more clear. So synchronous buck, right? We have a top side gate and a low side gate. And this is what we, oh, fuck. Okay, this is what we call the switch node. Because it's the node that is like being, that feels the most switching, whatever you want to say. And this is kind of like your V out. Let's say ground is 0 volts, right? And let's say our V out we're trying to achieve is like 5 volts. And let's say our switching chip, let's call this buck, I'll label it B for buck, can supply like, I don't know, 5 volts to these gate drive pins. Okay. So let's say we could have 5 volts here and 5 volts here. Now for the bottom FET, this is easy because we know for VGS to be positive, 5 volts minus 0 volts equals 5 volts. Does that make sense? That can conduct, like we're chilling on the bottom side. But, oh, our V out is 5 volts. And if our chip can only supply 5 volts to the gate drive pin, 5 volts minus 5 volts is not a positive number. We can't actually turn this top FET on. Did y'all follow up to this point? So for the bottom FET, we can turn it on with no fancy tricks because 5 volts minus 0 volts is positive. But since our switch node is biased to 5 volts and we have 5 volts on this gate drive pin, the potential difference here is 0 volts. We can't turn this FET on. We need a little bit extra juice in the tank, to speak colloquially. So what we do is add this thing called a bootstrap capacitor. I'll use a different color. I'll just draw this like over here. It's like a little extra like tank. If you think of current like water is like a water tower. And The top side is probably connected to some like internal regulator in here or like V in or something. But regardless, this capacitor is charging up. So when you try to turn on your bottom FET and you need that little bit extra juice, your capacitor will provide just enough to turn your FET on. And yeah, that's what the bootstrap capacitor is for. It's to bootstrap your top gate so that you have enough potential difference to conduct current on this side. That's as far as I'm going to go with this. If you want to talk more about it, we could talk about it later. But I just wanted to get that overarching idea out there. Does this like kind of make sense to people? Cool.
When people say bootstrapping, is this usually what it means?
For power converters, yes. Other terms, I don't know. Okay. And then scroll down, we look at absolute maximum ratings over operating free air temperature range unless otherwise noted. So free air temperature, probably room temperature-ish. Okay, so the input voltage can range from -3 volts to 19 volts max. Well, this is absolute max. And the difference you should know here is that your operating maximum is what, yeah, it's right here. It's what's recommended by the manufacturer, which means that they know for a fact that if you're within these bounds, your chip is probably going to do what you expect. As soon as you start creeping towards the edges and away from it, they're not really liable for what happens. 19 and -3 or -0.3 are probably absolutes in the sense that like maybe the silicon starts breaking inside the chip, or like there's just so much potential difference that you'd arc across something. Like basically something's gonna mess up inside probably. And they say that absolute rating is 19. If you wanted to test it and see if our battery, since it's 18.8 volts, if it like messes up the chip, that's only rated to 19 volts, you could try that. But like, unless you're really hard pressed on your bounds or like you need to pick this chip for whatever reason, I wouldn't recommend having your max, your absolute maximum so close to like what you'd potentially be working with. And then, yeah, you could probably read all these things. This is pretty interesting. Doesn't apply to us because we're not dealing with super high power, but this is like the thermal resistance of the pins in units Celsius per watt. If you need to worry about like, if you have so much power that there's a potential for like your solder starting to like melt, or your PCB traces get too hot, or you don't want the delta T in your whole system to get like too hot. Yeah, there's a bunch of stuff that you could read, but like what I always make sure to do when I first look at a data sheet, if I'm trying to get like just like a snippet of how it works, I look at this first page, I read the features, and then I try to look at this pinout page and get an idea of what's going on. And usually, like if it's for power converters, I like to look at the efficiency graph to see like, okay, I know I'm operating between 20 and 50 millivolts or milliamps, sorry. So we'll probably be in this range here. Lots of stuff in here. This is also another step deeper that I've started doing more recently, but I think is still not deep enough, like as ideal. If you want to have true understanding of like the circuit you're designing, you need to understand this and probably one level deeper. But yeah, this is the functional block diagram. And I don't know, maybe I understand like 80% of the symbols on here. Like, I don't know what this is. That's something XCon, maybe disconnect. I don't know. That's something that I have to look up in the future. But this tells you like how the chip is kind of working at a high level inside. So we have an enable pin that's going to some control logic. We have the feedback pin that's going to some control logic. And there's a voltage reference here. So that's, remember how I told y'all the converter itself needs some reference. So it could compare to see how your feedback is doing versus like what it expects. So it looks like there's some sort of comparator here. It's comparing the voltage reference to your feedback. There's also the soft start. Not really quite sure how that ties in. Ton one shot. I have no fucking clue what that is. TSD, the temperature thing, thermal something. OCL, over current limit. These acronyms, like you just get more familiar with over time. If you see OC, over current, UC, undercurrent, that's not really a thing. UV, under voltage, OV, over voltage. Yeah. So it looks like there's a comparator here checking for overcurrent. So there needs to be some sort of feedback for current potentially. It's probably internal. And if it detects your current is too high, this comparator will trigger. And then it'll affect the control logic in some way. We don't know what the control logic is because it doesn't say here. This is like the whole synchronous FET deal that I was talking about. You have your two FETs, and then you bootstrap it outside. Your control logic is also controlling the high side gate and the low side gate, LS, low side, HS, high side. And it looks like your VN, like I said, there's like tied to some internal regulator. And that internal regulator, let me add some colors, might make it easier to see. So we have VN, it's going to some regulator. It looks like the VREG is 5 volts or something. VREG 5, probably 5 volts. And then it goes here and it connects to VBST. And that's what charges your bootstrap cap. And then when you connect it to ground, like there's a way for current to flow, which will allow the capacitor to charge. And then this is also tied to whatever this high side gate drive is. So you have this input power plus this input power that can potentially source enough power to activate the gate of this top side MOSFET. Does that kind of make sense? We have our capacitor here that can dump a little bit of power. We have our control logic that's dumping a little bit of power. And someone did some math somewhere down the line so that it's enough to sufficiently power this MOSFET.
Can I ask a question?
Yeah, what's up?
Does the boost capacitor not connect to the switch pin rather than ground?
It might be the switch pin. I think it depends on the app note.
Okay.
It could very well be the switch pin on this one. I'm not sure. I could look, we could check. Yep, it is a switch pin. So yeah. Yes. Yeah, lucky you were correct. It's probably the switch pin on most applications, actually. I misspoke. Sorry. But yes. So looking at like the internals here can possibly give you a better understanding of how like some of these things are working, or you know more of the building blocks that go into these converters. And if you scroll down some more, sometimes it'll have some equations that'll tell you how to calculate specific values. So if we know the switching frequency that's provided in the data sheet, and you know your V in and your V out, you can calculate your inductance value for like your inductor that you need to spec. Usually if you scroll far down enough, it'll tell you a typical application. It looks like this is converting something to 1.05 volts at 2 amps. It tells you what inductor size, what capacitor size, all the good stuff. More equations for you to calculate like your resistor feedback thing. So you can see the resistor feedback network. Yeah, this is what I was looking for. Usually there's just a table that tells you exactly what to do, which is really nice. Makes your life pretty easy. So let's say we want 5 volts. R1 is 55K, R2 is 10K, and then tells you to pick an inductor. Yeah, nice. Okay. Spent a little bit too long on this. Oh, one more thing. It also tells you how to lay out the PCB exactly. So this is your chip, tells you where to put your bootstrap capacitor, tells you where to put your inductor and your bypass capacitors and all that good stuff. And usually this is sufficient unless you're like super constrained for space on your board, or you know that you need to put something like right here for whatever reason. You could probably just copy the layout example. Yeah. Okay, we dwelled on that for a while. So we have to go through this at some point. But how about this? Let's just open up another one, just to see if the process is similar for like a different manufacturer. Like, how does the datasheet differ? So usually look at features. Adjustable from this, or fixed at this. Okay, so this is our output voltage range. So unless we're trying to operate under 5 volts, I'm not sure if this buck will work for what we want. This is a buck, right? Yep. Synchronous rectification. So synchronous immediately points out and says there's probably 2 MOSFETs inside the package. The input voltage range is from 2.7 to 5.5 volts. Okay. I guess this would be like a second stage kind of thing. If we want to have a super like a isolated kind of like low output rail deal. Lead free, if you're into that. Okay, it tells you some of this. But yeah, here's the usual pin description. Tells you the pin, and then the pin name. This is cool. It tells you if it's an analog or yeah, what type of input it is. That's cool. Enable for switching regulators, active high, turned off by logic low on this pin. Pin is ground reference for the NFET power stage analog section of the IC. Pin must be connected system to ground. Okay. Connection from power MOSFET to the inductor, switch node. Okay. So yeah, like most of this is pretty similar. I think what's pretty interesting here is that they have a PFET for one of the MOSFETs, and the pin is decoupled to ground by a 4.7 microfarad capacitor. So I'm not quite sure what the looks like this. So we have our P-type MOSFET here, and we have our N-type MOSFET here. This is your switch node. And because you have a P-type MOSFET here, you don't need a bootstrap capacitor. We still need a bypass capacitor for your V-in, but that's because like we usually have some sort of bypass capacitance on ICs. But yeah, you look at the functional block diagram, you see that a lot of it is kind of similar. There's your enable, you have like your current limit, your feedback, some comparators here, some logic for controlling whatever, internal voltage reference, all the bells and whistles. A lot of it will be similar. But yes, this is how you read a data sheet. I'm sorry, this might have been a little bit dry, but I think it's a very important skill that you develop over time. Okay. Enough about that. Let's talk about KiCad for a second. So I think that doing schematic work can potentially be very easy for multiple people. Layout work might get a little bit hairy. What I'm the most afraid of is like, since there's, only one file, someone opens the file, makes a bunch of changes, pushes those changes, someone else is working at the same time, and then they accidentally like, I don't know. I don't even know what you could do, but somehow the changes get overridden, there's a merge conflict or whatever, and someone's going to be left unhappy. Probably 2 people, because one person has to address the merge conflict and then one person has to deal with the work being lost. There probably has to be some sort of like system that we enact, because KiCad is limited in its functionality. There's PCB design tools where it's like Google Docs, and like multiple people can be working on different things at the same time, which is super cool. But those are expensive, and we don't have those. Okay. So what I'm envisioning for KiCad, or at least this workflow, is that each of us or each of y'all have your own schematic sheet, and you only mess with your schematic sheet. Like, don't open anyone else's, don't click on anyone else's. Just mess with yours, and then push that every single time. Push that to Git. Now you can open other people's sheets. Sorry, I don't want to say that you can't open it, but don't make changes and don't push that. You have to push your sheet only. And I think on KiCad, you can have like page trees with multiple sheets, so that like it's separate files. So Adi's schematic is his own file. Izzy's schematic's her own file. She's schematic's her own file. That'll make the schematic work great. If that's how it works, that'll be phenomenal. If it's not, then we'll have to figure something out. For layout, I think that's where it starts getting really hairy. We'll probably have to schedule something and have backups of like all of the progress, which sounds very unfortunate, but we want to try to figure out if there is some new way that we can have multiple people collaborating on a project. And for better or worse, we're the ones figuring that out, and we might have some bumps and blips along the way. Yeah, let's actually click around and see if we can have multiple files for schematic pages in KiCad. Again, like I mentioned at the start of the meeting, I just know what I want. I don't know if I can do it. So create project. Oh, I already made one of them. Sick. Okay, that's not what I want. File, new. Okay, let's open this up. Oh, wait, I think I saw it. What is this? Page layout editor. New page layout design. Oh, that's not what I wanted. Okay, let's open the schematic and see what we can do. Schematic hierarchy. That sounds promising. Okay. So we have a root folder, file. Okay. Maybe not edit, file. There's a solution we could do for this. Google it. How to have multiple sheets in KiCad. Multiple sheet schematic. That sounds like exactly like what we need. Okay. Place hierarchical sheet. All right. Place. Okay. Let's put this down. Oh, okay. File name test.sh. That's what the tag is. I don't. Okay, I'm just gonna leave that because I don't know what it is. Oh, and now we're on a new page. That's kind of dope, actually. Wow. All right. That's good shit. Okay, so let's see if something actually changed in the files. So this is in documents, formula. Power research? Yes. Okay. So there's still only one schematic file, but there's multiple pages in it. And I don't know what that means for us. Let's go back to this page tree. Okay, so we have a test page. Oh, that goes up a level. Cool. Okay, let's make another page. Let's see what happens. Place hierarchical sheet. Test 2. Whoa. I have my test 2 sheet also. Let's try something. Let me hope KiCad doesn't crash. Okay. And let's put down a resistor. Let me save that. And now, open a terminal. Documents, formula, power research. Okay, can someone fork this repo and pull it to their computer? So like github.com. And literally anyone can do this. And then you would probably click on Mark V boards or something because that's what you have. And then you go to Olin Electric Motorsports. Is anyone following? Does anyone have the...
I'm in Windows right now.
Okay, just go to... Oh, okay.
Same.
It's okay.
I can do it though. I can do it. I don't know if KiCad.
I can do it. I'm on Linux.
All right. Lucky, you're
Thanks,
gonna
Lucky.
have to... Yeah, thanks, Lucky.
Okay.
Can you clone the power research deal?
Yeah. Sorry, one sec.
No hurry. I'm kind of nervous about this. Is it gonna work or is it not?
Cool idea.
If it works, it'll be legendary. If it doesn't, it's just gonna be a sad attempt at making it work.
Yeah. What's funny is like, I bet with something fancier like Altium, they just like have this like worked out. But
Yep.
what's funny is we don't use something like Altium because then we have less control
Yep,
over like fixing issues. But it's funny because then you can sacrifice like a lot of functionality.
for sure. Like the software we use at work this summer is like Google Docs, literally. Like someone places a resistor and then you're looking on your computer and the resistor just shows up. It's magic.
What's it called again?
It's called Expedition. It's by it's from the Siemens company. They make a lot of science techy cool stuff, cool tools.
Okay, I have it. What did you want me to check in this repo?
Okay, can you open it? Like, can you open the schematic?
Yeah.
And then go to test 1. And then just like place a component down.
Okay.
And I'm going to place a component on test 2.
And we're gonna see if we get a merge conflict. Is that what the
Yep.
idea is? Okay.
So yeah, go ahead and place like a resistor or whatever, and then push it.
Okay, so I'm doing test 1, right?
Yes.
Oh god, I haven't used KiCad in so long. Wait, wait. There is no test 1. You mean just test?
Yeah. Sorry.
Okay.
Poor instruction.
Oh, what's a photoresistor? So should I do save or save current sheet? What do you think?
Whoa, you can do that? Yeah, save current sheet, whatever that means.
Okay. Let me go check my repo and see what files changed.
I would imagine just a schematic file, maybe your cache.
Yeah, it added that like skib back file. You know what I'm talking
Yeah, yeah.
about? Okay, I'm gonna close KiCad then.
And then can you commit that? Can you just push directly?
I can see.
GitHub looks different these days. Looks a little more material design.
Yeah, it does, right?
It's kind of,
It's been a hot sec since
I
I've
think it
been
looks a
on
little more
GitHub.
bootstrap.
yeah.
Okay. All right, I'm gonna add and push.
Do it.
Okay. Okay, it looks like it pushed.
Okay, let me, yes. Okay, so now I have my schematic stuff saved. Let me go to terminal and get pull. Okay, okay, so that pulled. Now let's see if it fucked up whatever's going on here. Let me close KiCad. Maybe it's open. I'm not optimistic, but let's see. Oh, okay, okay, okay. Oh, let's fucking go. That's some good shit. All right. All right, guys, I'm fucking hyped. This is good shit. All right. And now I should just theoretically we made it. This is the single greatest thing to happen to this team, other than a lot of other things, but this is good shit. Okay. If y'all are not 100% sure about what just happened, I was able to change the file on my end. Lucky was able to change the file on his end without touching each other's. And then we were both able to push it, and there was no problem, which means if we don't fuck this up, all of us will be able to edit our own sheets in KiCad, and we'll be chilling. Okay. There's something else I'm wary of.
Hey, Adi.
Yeah.
I'm just looking at the commit you just made.
Yeah.
And you committed test.skibak, which should be mine. Did you just add all, or what did you do before you pushed?
Yeah, I get added all.
Oh,
Wait.
okay. Because you see like the commit message, the
Yeah,
most recent commit message for test.skibak is fuck yeah, this worked.
Yeah, but test.sk is still lucky test edit test.
Well, that's how it should be. Like my files on test.sk and test.skibak should be always only commits that I made. You should
Sure.
never commit changes to either of those files, right?
Yes. Yes.
Like you should have done git checkout test.skibak before you push, before you
Yes.
added your changes.
I should have. Yes. I should have only committed test2.sk and test2.skibak.
I mean, we can demonstrate fixing that right now if you want to. Like you can soft reset and then check it out and then force push the changes to remote if you want to. I don't know. It's up to you.
Lucky, I'm not a Git expert. We can figure this out offline and
Yeah,
we can have a proper demo.
It's gonna work though. It
Okay.
seems like.
I trust that. I think we should write a Confluence page on how to make sure we don't fuck this up, and then we can move from there. But go team! This is exciting. I don't know if y'all could tell, but I'm really excited. This is good shit.
I'm not 100% sure, but I think like so you opened his file, but then like you didn't close it. Like I don't know, you still have KiCad open. Whenever I commit anything, like I never have KiCad open. But so sometimes when you like close somebody else's thing, it'll like ask you if you want to save, even if you didn't make any changes. So if that happened here, you probably could pick don't save, and then it wouldn't have changed.
Yeah,
Possibly, I don't know, but
when you're Git adding, I did something bad, and I did Git add dot, which means you're adding everything in the directory. But you could select like the specific files. Like if I want to do test2 dot. Okay, I mean, oh, I need to go into a folder. Okay. Instead of dot, I could do test2.shkabak or whatever, and only add that file. So I think we might have to be a little bit more diligent about what we're adding and committing, but yes. Lucky definitely knows more about Git than I do, so if I say anything wrong, just definitely call me out.
No, I mean, you're totally right. I mean, the important thing to know is like, as long as they are actually separate files, it's impossible to not be able to fix it with Git. It's like no matter what you do to someone else's file, if it's a separate file from yours, it's very easy to just say undo whatever changes I made to that before you add and push your changes, add and commit and push your changes. And even if they are the same file, you can still like work it out, but it just gets a little more complicated. But like, yeah, so like even if you accidentally like click save this other person's schematic before you add your changes, you can undo that change very easily in the command line using git checkout.
Yes.
gotcha.
And like if you type git status, it actually tells you here's how you undo this change. It'll say type git checkout this file. But yeah.
But yes, since I just
Well, you have to have some changes.
Yeah, I need to have changes. Regardless, not important. That's all I really had today. I hope y'all learned a little bit about reading data sheets and kind of what the process is moving forward for us when we're picking a component. And also, I'm excited that this worked. I'm curious as to why the sheets don't show up in your little side thing here for your schematic sheets. But I guess, I mean, they show up in the schematic, which is cool. That's pretty tight. I'm pretty excited about this. All right. Thanks all. If you have any questions about what we discussed today, or you want to offline it, just Slack me or put it in the Power Coupons channel. And yeah, I'll see y'all sometime.
Sweet. Thanks.
Thank
Yep.
you.
And we're gonna get started on design work real soon. So stay tuned. Lucky, what do you think about that?